another episode of Math in the House. I'm your host, Dr. D. We're about to embark on Chapter 2, Section 1, the slope of a tangent. Okay. Now, we're starting in Chapter 2, basically because Chapter 1 is a review of your math analysis, functions, that kind of thing. Now, if you guys had a mediocre math analysis teacher, then we'd have to do Chapter 1 now. But I have first-hand knowledge that your math analysis teacher was phenomenal. So, we're skipping Chapter 1 because you guys don't need it. Chapter 2. All right, the slope of a tangent. Now, a tangent, we're not talking tangent as in trig class, we're talking about tangent as in a line that intersects a curve at exactly one point. So, if I have a circle, that's a circle. Now, a tangent to the circle would be a line that intersects that circle at exactly one point. There it is, there's your tangent to the circle. Now, I could also have any kind of curve. So let's say we just have a curve like this, and I want to know what the tangent at this point looks like. Well, that's going to look like that. There's a tangent to that curve. Now, we're interested in finding the slope of this tangent. But we have a problem. The tangent is defined by exactly one point. But we know to get the slope of a straight line, we need 2 points, because we need change in y divided by change in x. There's only 1 point there. Problem. Okay, so here's what we're going to do. We're going to manufacture a second point. All right, let's say we have a parabola. So we have the equation f of x equals x squared, or y equals x squared. Now we want to know the slope of the tangent right here at point P. So what we're going to do is we're going to manufacture a second point so that we can get change in y over change in x. So my second point well, first of all, here's the tangent segment. The black line is the tangent segment to the point at P. And our goal is to find the slope of this tangent, which the computer is telling us it's 2.005, but how do we know that's true? Okay, so we're going to, like I said, make a second point further up the curve. That means we're going to have some distance away from x that's h. So this distance from x to x plus h, that's going to be h away. So that's basically, we say this distance is h from here to here. So I have this point x and this point x plus h. Now, next thing I want to do is create a point that's got the x value of x plus h. So my x value would make the point right here on the curve. We'll call that Q. So notice point P is x, comma, f of x. Point Q is x plus h, comma, f of x plus h. So the x value, the y value for P. Now we've got the x value for Q, which is x plus h, and we've got the y value for Q, which is f of x plus h. All right, now, what's my slope of the secant? Now, what's a secant? Right, it's a straight line that goes between 2 points on a curve. So my secant, PQ, is going to be, now, this slope of PQ is going to equal the change in y divided by the change in x. So what's my change of y? Well, it's f of x plus h minus f of x. And what's my change in x? X plus h minus x. So that's my slope of PQ, f of x plus h minus f of x, all over x plus h minus x. Well, x plus h minus x is just going to be h. So this is going to equal f of x plus h minus f of x, all divided by h. Now, what is my f of x? It's x squared. So, yeah, we'll just leave this like this. F of x plus h minus f of x over h. Now, let's say we make P 1, 1. Now, for some reason, this program will not let me go 1, 1. It's going 1.002 and 1.005. But we're going to call this 1, 1. And now, let's say we make point Q 2, x equals 2. So what's the y value? Well, it's got to be 2 squared, which is 4. So now if I have these 2 points, then the slope of PQ is going to be 4 minus 1 over 2 minus 1. So we'll say the slope of PQ equals 4 minus 1 over 2 minus 1, which equals 3. So it doesn't equal 3.005 according to our points. It equals 3.005 according to the points in the book. But that's the slope of my secant. Now, does that look like the slope of the tangent? No, it doesn't. It's steeper than the slope of the tangent. See, the black line's the tangent, the green line is the secant, but because I needed a second point, my secant line is steeper than my tangent line. Okay, so what we want to do then is we want to say the slope of the tangent is going to equal the limit as h approaches 0. In other words, as I let Q get closer and closer to P, then notice my secant line will get closer and closer to my tangent line. So here's what we do. We let h, the distance between these 2 points, h is the distance from P to Q, which in this case is 1. We're letting h approach 0. Okay, so watch what happens. as h approaches 0, notice the slope of the green line is approaching the slope of the black line. So notice as h approaches 0, notice we're going x plus h, well h gets smaller and smaller and smaller. Now as h approaches 0, then the x plus h and the x are the same point, which means the p and the q are the same point. And that will give us the slope of the tangent. So notice the slope of the tangent is 2.005. As we slide q closer and closer to p, then the slope of PQ gets closer and closer to 2.005. Okay, so what we just found out is we can't get the slope of PQ when P and Q are the exact same point. Otherwise, we don't have a slope. We don't have a change in y over a change in x. But what we want is the limit as h approaches 0. And when we get that limit as h approaches 0, then we're going to get the exact slope of the tangent to as close as we want. Okay, now, the derivative, or the slope of my tangent line, is the limit as h approaches 0 of f of x plus h minus f of x all over h. You're going to want to remember that. Okay, so let's get to our book. Check out page 87. Now, notice example 1. Find an equation of the tangent line to the parabola y equals x squared at the point 1, 1. Well, okay, this is the thing we were trying to do, the point 1, 1. Well, I'm making some other point, q, and we don't know where q is. So we're just going to call it x squared. Okay, so here's our point q is right here, and it's going to be x squared. Notice it's x comma y. Now, and it's on this parabola, so whatever x value goes in, the y value is always going to be that value squared. Now, the slope of PQ is going to equal the change in y divided by the change in x. So what's change in y? X squared minus 1. What's change in x? X minus 1. So what we want is the limit as x approaches 1 of this thing. So the slope of PQ is really the limit as x approaches 1 of x squared minus 1 over x minus 1. All right, now let's see how that works. Notice on page 88, you have a table in the blue. So when x is 2, then your slope is 3. And that's what we just did before. If x is 2, then I've got 4 minus 1 over 2 minus 1, which equals 3. Now, what we're going to do is we're going to slide q closer to p, which means we're sliding x closer and closer to 1. So we started with x equal 2, but we want to move that closer to 1. So we're going to make it 1.5. So if you notice, 1.5, plug in 1.5 for x, and you get 1.5 squared minus 1 over 1.5 minus 1, and you end up with 2.5. Now you plug in 1.1 for x. 1.1 squared minus 1 over 1.1 minus 1. That's going to end up being 2.1. Now we go even closer. We're going 100th away, 1.01. Now when I put in 1.01, square it, subtract 1, 1.01 minus 1, divide, that's going to give me a slope of 2.01. And when I put 1.001, only 1,000th away, when P and Q are 1,000th away, then the slope of PQ ends up being 2.001. Now, what if I make Q a point down below P, or in other words, to the left of P? Well, now we could say, okay, let's let Q be right here at 0. Well, that's easy to figure out. If the change in y is 1 minus 0, and change in x is 1 minus 0, so that's 1 over 1, which is 1. So the slope, if we let Q be at 0, would be 1. Now, if we let Q slide closer and closer to P, in other words, we're letting this h value get smaller and smaller, then, or we're letting x approach 1 from the left, then notice what happens. You put in 0.5, your slope is 1.5. You put in 0.9, your slope is 1.9. You put in 0.99, your slope is 1.99. Put in 0.999, once again 1,000th away, and your slope is 1.999. So if you look at the figure 3, you see that on the top row, Q is approaching P from the right. Now, on the bottom row, Q is approaching P from the left. Either way, the slope of the secant, PQ, gets closer and closer to the slope of the tangent. Now, we can figure out the slope of the secant anywhere we want, but we don't know the slope of the tangent unless we know the limit as h approaches 0. So, this is basically what we have. The slope of, let's just go slope of the tangent. Slope of the tangent equals the limit as h approaches 0 of f of x plus h minus f of x over h. Now notice, you can't just plug in h equals 0. You have to put smaller and smaller h values in there. And then what you do is you look and say, okay, if I'm approaching from the right, then the slope goes 3, 2.5, 2.1, 2.01, 2.001. What's the slope approaching? Well, it looks like it's approaching 2. If I approach from the left, I'm going slope of 1, 1.5, 1.9, 1.99, 1.999. What is that slope approaching? It's approaching 2 also. All right, that means the closer we get, the closer we make Q to P from either direction, the closer the slope of PQ is to exactly 2. Now, can we prove that the slope at P, the slope of the tangent, is exactly 2? Watch the magic. Okay, so we're saying the slope of PQ is the limit as x approaches 1 of x squared minus 1 over x minus 1. Well, can we factor the x squared minus 1? Yes, we can. So this equals the limit as x approaches 1 of x plus 1 times x minus 1 over x minus 1. All right, now the x minus 1's cancel, so this equals the limit as x approaches 1 of just x plus 1. Now, as x approaches 1, x plus 1 is going to end up approaching 2. Bam! So the slope of the tangent at point P is exactly 2. Now, here's the deal. In order for us to understand how to evaluate the slope of a tangent to a curve, we need to understand how to deal with limits. Now, fortunately for you, I've been talking about limits since you were in Algebra 2. So this is not a foreign concept that it would be to some poor math students that didn't have quite a phenomenal teacher as you have. But now we really need to dig into the idea of how to evaluate limits, and that's going to be what we're going to do for the rest of this chapter until we get to the definition of derivatives. So, let's check out page 89. Okay, now this is the same example, or the same idea, with just different numbers. Okay, the flash on a camera operates by storing a charge on a capacitor and releasing it suddenly when the flash is set off. The data at the left describes the charge Q remaining on the capacitor, measured in microcoulombs, at time t, measured in seconds after the flash goes off. Use the data to draw the graph of this function and estimate the slope of the tangent line at the point where t equals 0.04. The slope of the tangent line represents the electric current flowing from the capacitor to the flash bulb, measured in microamperes. All right, so they're giving us that at time 0, at the beginning of this problem, you've got a capacitance of 100 microcoulombs. Now, 0.2 of a second, the capacitance is going down to 81.87. Then 0.4, it's 67.03, and it goes down all the way to 1/10 and 36.76 microcoulombs. So notice what they did then was they graphed this relationship in the red curve. That's my red curve here, is that relationship of the flash bulb, the capacitance of the flash bulb at each time from 0 to 0.1 seconds. Now, what I want to know is the slope of the tangent at exactly 0.04 seconds. So that's my point P. So how do I find the slope of that tangent? Well, what I'm going to do is I'm going to take the slope from P to R. So basically I'm taking the slope from the from 100 to 67.03, and that's going to be x from 0 to 0.4. So that's basically the slope from point Q to point P. And then I take the slope from point R to point P, and I average those out. So notice what they did was they found the slope from P to R ended up being negative 824.25. The slope from Q to R ended up being let's see, where are we here? Negative 742. So when you average those two out, you get negative 674.75. And so basically we're estimating the slope of the tangent line to be that average between the slope to the left and the slope to the right. Basically what you could do is, it would actually be easier to take the slope from A to P and then the slope from P to C and average those two slopes. And that would give you the approximate slope from A to C. Let me make sure you got that. If I take the slope from A to P, and that's a slope of a secant, and then the slope from P to C, that's the slope of another secant, and I take the average of those two secants, then I have the slope, the approximate slope of the tangent. Let me show you that. Okay, here's my curve. And we'll just say, we'll call this point P. Now this is point A and C. So here's point A, here's point C. Now, if I take the slope of the secant from A to P, and then the slope of the secant from missed. Okay, so I take the slope of the secant from A to P and the slope of the secant from P to C and average those two slopes out, then what I'm going to get is approximately the slope of the tangent. Notice these two slopes here, we'll call this the slope from A to P and the slope from P to C. So the slope of the tangent is approximately equal to the slope from A to P plus the slope from P to C divided by 2. The average of these two slopes gives me the slope of the tangent. So that's basically what they're doing there. Now, the last example, they're doing a velocity example. Now, when you were in Algebra 1, you were told that velocity equals distance divided by time, or distance equals rate times time. The problem is, velocity changes. Like, you don't just get on the freeway at 85, no, you never get on the freeway at 85 miles an hour. You get on the freeway at 30 miles an hour and you speed up to 65 miles an hour. So your velocity doesn't instantaneously get to 65 miles an hour. So what we're dealing with now is a changing velocity or a changing slope. So you notice this red curve. There's a changing slope at whatever point we want. If I pick a point up here, my slope is steep. If I pick a point down here, my slope is more gradual. So same thing with velocity. Sometimes velocity is large, sometimes it's small, but it changes gradually. So there's no instant where, or there's no you're not going to have the same velocity through the entire trip. Okay, so suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. So the average velocity is the distance traveled divided by the time elapsed. That's going to be your average velocity. But we don't want the average velocity, we want the instantaneous velocity at exactly 5 seconds. Well, what I can do is I can find the velocity at between 5.1 and 5 seconds. And that's what we have here. Distance traveled would be s of 5.1 minus s of 5. That's the distance it is at 5.1 seconds minus the distance at exactly 5 seconds divided by 5.1 minus 5, which is 0.1. Now, if I go the other direction, so that gives me 49.49 meters per second. Now notice, that's a 1/10 second difference to give me 49.49. Now if I use if I go from 5.05 to 5, so I'm only at a 500th second difference, then my average velocity is 49.245 meters per second. If I go 100th difference in a second, then my average velocity is 49.049. If I go 1,000th difference, my average velocity is 49.0049. So what it looks like is my velocity at exactly 5 seconds is going to be 49 meters per second. And that's what we have here. The slope of PQ is going to be the slope, the change in y divided by the change in x. So there's your, the exact same formula that we had in the first place. All right, so that's what we're doing today, is merely plugging in values closer and closer to the value we want and seeing what that does with the slope. So it's really crude. What we're doing right now is just getting your feet wet, just getting you to understand what the concept is that we're letting a certain distance approach zero. That's the whole idea of a limit. So that's it. Have fun with these.